Hello Algebra 2 students. Today's video will review your Day 5 notes which introduced irrational and complex solutions. So first we're going to think about the numbers that we know about. We know about integers. Integers can be positive numbers like 2 or 100, and they can be negative numbers and they can be 0. So they could be like -5 or 0. So some people think of them as like whole numbers, but whole numbers that are positive, negative, and include 0. Not integers could be fractions or decimals like 2/5, 1.7, and they can be negative as well, -0.235. And they can be decimals that go forever if they repeat. So 0.3 repeating is a rational number as well. And we know that they're rational because they can be made into ratios. So 2/5 is obviously already a ratio. 1.7 is the same as 17/10. So that could be a ratio. Any number that's a decimal can be a ratio by putting it over its place. So that's 2/10, 23 hundredths, 235 thousandths. So this would be -235 over 1,000. And then this decimal right here, 0.3 repeating, is the same as 1/3. So anytime you can make the number into a ratio, it is a rational number. Irrational numbers are numbers that go forever. The decimals will go forever, but they don't repeat. And one example that you know pretty well is pi. So some of you may have memorized several decimal places of pi, but we don't know all of them. Over here, this category has not been defined yet. We'll get to that later, but remember there's real numbers and then there's something else. All right, so we are going to solve this equation by factoring its difference of squares, and that follows the pattern a squared minus b squared equals a minus b times a plus b. So when I factor this, I get x minus 6 times x plus 6 equals 0. And since the product of these factors is 0, one of these factors has to equal 0. So you set them each equal to 0. This one gives me x equals 6. And then x plus 6 equals 0. This gives me x equals -6. So there's two solutions. And it says to check by graphing. So we're going to open up Desmos and graph. So in Desmos, I graphed x squared minus 36, and I'm looking for the places where this equals 0. So the y is 0 here and here, and that's exactly what we got by factoring. Okay, going back. These equations down here are not factorable, and so we're trying to figure out if we could solve either of these. This one kind of looks like difference of squares, but the 2 is not a square. For this one, we would be looking for numbers that multiply to -3 and add to 1. And there aren't any numbers that multiply to -3 and add to 1. So for this one, we're still going to have to be on the fence. There is a way to solve it, but we haven't learned it yet. For this one, we could try graphing it. X squared minus 2. We could actually try graphing this one as well. But let's try graphing x squared minus 2. Okay, and so we're going to get these two answers here, -1.414 and positive 1.414, but those are answers that Desmos has rounded for us, and those are not exact answers. The decimals actually go on forever. These are irrational answers, but we don't know the exact answer for these. So I'm going to put this on the paper that we tried graphing. And when we graphed it, our solutions were x equals -1.414 and x equals positive 1.414, but they're not exact. And we know they're not exact because I'll substitute the positive 1.414 for x to see if I can get 0 out of it. So I'm going to go back to Desmos and I'm going to try that. Okay, so it gets me really close to 0, but it's not exactly 0. It gives me -0.000604. Okay, so it's close, but not exact. So to find the exact answer, we could try to solve by getting x by itself. And that's the reason why we're not doing this one, because this one has two different kinds of x. But this one here has just a single x squared term. So I'm going to write the equation down. And I'm going to try to add 2 to both sides to get x squared equals 2. And then I can solve with a square root. But when you solve with a square root, you have to remember that you can square a positive number or a negative number and get the same result. So the answer could be positive or negative. So what I get is x equals positive root 2 or negative root 2. And if you check that answer, when you put it back into your equation, if I square the square root of 2, squaring and square root cancel out, so I get just 2 minus 2, which is exactly 0. So getting that x squared by itself and solving with a plus or minus square root worked for us. The thing about root 2 is that it is an irrational number. So we can't give a decimal approximation, we have to leave it as root 2. If you want to put root 2 into Desmos, it does give you a lot of digits, but if you look at the digits, they don't continue to repeat. I can see the 1414 here, but it doesn't continue to repeat. So this is not a rational number. It has to stay as root 2. So I could add root 2 and negative root 2 to my irrational numbers. All right, turning the page. For a quadratic equation, usually we find that there's 2 solutions because there's usually 2 x-intercepts. There's just one way that you can make one solution, and that would be when your vertex lands right on the x-axis, and then you could have just one solution. But usually you're expecting to see 1, 2 solutions. So usually 2, and sometimes 1. So we have to remember that when we're solving, that we're usually going to find 2 solutions. So I'm going to solve this by isolating the x squared. So I'm going to add 20. And I get 5x squared equals 20. And then divide by 5. And I get x squared equals 4. So remember that there's 2 solutions here, because I know that I can square root this, plus or minus, and I'll get 2, so I'll get x equals 2, but x can also equal negative 2, because negative 2 squared is also 4, so plus or minus 2. When we do c, I'm going to add 7, x squared equals 7, and I'll do plus or minus square root. And this time, for the square root of 7, it does not come out to be an integer. It's also an irrational answer, so I just have to leave it as root 7. So if we're thinking about more irrational numbers, we could put root 7 and negative root 7 as irrational numbers. All right, when we get to D, we're going to have an extra step. So I get x squared equals 12. And I'll square root both sides, and I get x equals plus or minus root 12. But root 12 can actually be simplified. And you can simplify radical when the number inside has a perfect square factor. So I can't do the square root of 12, but there's a factor of 12 whose square root I can do. One way to find these perfect square factors is to make a little factor tree. When a number comes up twice, you know that there's a perfect square factor. So I'm going to rewrite 12 as 2 times 2, which is 4, and then times root 3. So I have the square root of 4 times the square root of 3. That's going to give me the square root of 12. And then plus or minus, I do know the square root of 4 is 2, and then times root 3. So this is my simplified answer. All right, we're going to go on to E, and in E, I'm going to subtract the 9. I get x squared equals negative 9, and x equals plus or minus the square root of negative 9. Now I'm in a little bit of trouble because I know the square root of 9 is 3, and I could have If it was just a positive 9, I could have a positive 3 and a negative 3. But there's no number you can multiply by itself to give you negative 9. And because of that, mathematicians defined the number I, and the number I is defined to be the square root of negative 1. So that's a new number for us, I. Defined to be the square root of negative 1, so I could simplify something like this. So I'm going to take my negative 9 and split it into negative 1 times 9. And then the negative 1 will be the I, and the square root of 9 is 3. Okay, so we're going to finish this one up. I times 3, usually you put the 3 first, so I have plus or minus 3I. All right, so this is an imaginary number. I is an imaginary number. If I know that I is the square root of negative 1, I also know that I squared equals negative 1. So then on the front of your notes, we can put imaginary numbers. They're actually a subset of complex numbers. Complex numbers. And so we know one of them is I, and we just also found 3I and negative 3I as imaginary numbers. Okay, and then the list of the first 12 perfect squares. These are just perfect square numbers that are going to help you when you are trying to simplify a radical like root 12, so that you know what kind of numbers you're looking for, like 4 in this case. 2 squared is 4, 3 squared is 9, 4 squared is 16. So you should try to make this list on your own, but I'm also going to make it now. 6 squared is 36, 49, 64, 81, 100, 121, and 144. Okay, and if you can think of any other numbers to add to your graphic organizer, you should do that.